Hello everyone and welcome to this presentation. My name is David and I'm a structural engineer, and in today's presentation we are going to dive into seismic analysis using TSD, and that is in full compliance with Eurocode 8. I'll be showing you how to set up your building, define seismic loads and mass source, and also select the right structure type, interpret the results, and this is to make sure that your design meets safety and life safety requirements. So whether you are a student or a practicing engineer, it's a privilege to be here, and you're going to learn a lot. And so let's dive into it. So I have my model here. I've modeled this structure. It's an 8-story building. It's a commercial building, and I have done everything for the project, including the detailing of the structure. You can see the slabs here, and also the beam layout plans and all this, and also the beams here. So this has all been done perfectly, and everything has been documented as per the requirements. So, and yeah, these are the lifts and all that. So you look at this, and we're going to learn something. So before you proceed with seismic analysis, the first thing that you must do is that you must first of all define and make sure that you have defined all your normal loads. You can see here I've defined all this, the dead load, the imposed load, and all this. So what you have to do now is to proceed with the remaining part, which is now the defining of the lateral forces of the seismic and the wind loads. So you can see my model is okay if I validate, and I have applied all the loads. And the reason why you should first of all apply the loads to the structure before you proceed to seismic analysis, it's because, as you know, seismic or mass source is calculated from normally calculated from the total permanent actions, and you add a percentage of variable actions. So it is important for you to first of all load your structure, so that when now you shall be calculating your mass source, you're going to have the structure fully loaded. And as you can see here, according to Eurocode, you can see this is how you calculate the mass source. It is permanent actions added to a percentage of variable actions. And for the residential buildings and the office buildings, we normally use 30%, which is about 0.3. So that's why it's imperative for you to load your structure. I hope you can see all this. This is according to the Eurocode 8. This is how you define your seismic mass. Now let's proceed. After you have defined all this, you should proceed now to this wizard here called the seismic load, and you come to seismic wizard, and they are going to go by the code spectra to period, and we go to the next. Then here we have these details here. The first detail here we have is the height to the highest level, which is 24 meters for this case. And the second thing here, the software is asking you to choose which part of the floor you're going to ignore the seismic, something which is also very important to pay attention to. because as you know, the basement uh, does not really contribute to the vibration when the seismic is in action. So in this case, in our case, it will be important for us to select the basement or the base as the floor where the software can ignore the seismic flow. And it is important to understand this, because if you don't do this, the software is going to give you some errors, and it is going to result to destabilization of your structure. So it's important to understand all this when you are doing your design. And as I have said, uh, it is usually the upper floors that contribute largely when it comes to the seismic or the seismic forces. So when you're calculating the mass source, we normally consider uh, the floors that are above the basement. And as you can see here, we also have another thing here called the reference peak ground acceleration. And all this data here is important because it is what that contributes to the masses. And according to Eurocode 8, the number of modes to be considered shall be such that the sum of the effective modal masses for each direction amounts to at least 90% of the total mass. All right. So it is important to get to understand all that. So when you look at this, we have the reference peak ground, and this one depends on the data that you have. For example, if you you're in East Africa, you can consider East African Rift Seismic Studies and the regional hazard assessments to get reliable data for this. And considering that we are in a low seismic zone, we would consider 5%, and that is according to East African Rift Seismic Studies that has been conducted. And when you come here again, we have the importance class, and this is also important to highlight here. So you can see I have mentioned about this here, and the Eurocode is very clear about this. The importance class, we have about 4 of them. We have number 1, the low consequences, and these are normally for agricultural buildings. And number 2, we have the ordinary buildings, and we have also for the high occupancy buildings like the schools and the offices. Number 4, we have the essential facilities like hospitals and fire stations. So in this case, we are going to consider case number 3 for higher occupancies. So we are going to take this as number 3. On the other hand, we have two type of spectrum type. We have type 1 and type 2. And type 1 is normally for high seismic zones. Type 2 is for low seismic areas. So we have this importance spectrum, and I'm hoping to show you this here. It's normally divided like that, and yeah, it's important to understand all that, and you can always refer to your Eurocode when you are doing your design. So that is it, and you can see we have all this defined here on the Eurocodes. So let's proceed. So we have this type 2. Okay, now this is good for you to understand that ground acceleration is normally a multiplication of reference peak ground acceleration and the importance factor. So in this case, you are getting 5% multiplied by 1.2, you're getting 0.5. The software is calculating by itself. And it's also important for you to understand that we also have what we call the spectral acceleration. And spectral acceleration is how fast the building is moving back and forth when subjected to seismic forces. While on the other hand, the ground acceleration is how fast the ground under the building is moving back and forth during seismic actions. And this is important to understand because it is what we use to calculate the seismic force. You know, force is calculated as a product of mass times action, and in this case we are considering force is an equivalent of mass of the source mass of the building multiplied by the spectral acceleration and fundamental time. And the fundamental time is the oscillation period that is taken by the building to move back and forth when it is subjected to seismic force. And as you can see here, I have showed all this, how you calculate the seismic force according to Eurocode. You have this. This is how you calculate all this. It is important to understand that. And also this is how you calculate the fundamental period according to Eurocode 8. You have this factor, the 3/4 of the height of the building applied by the structural system coefficient, normally 0.75 for RC frames and 0.085 for steel structures. So it's important to understand all this. So we go to ductility class. We have low ductility, we have medium and high. So when it comes to ductility, it is also important for you to understand that ductility refers to how best the structure can dissipate the seismic energy. So we have low ductility, we have medium ductility, and we have high ductility. So for this case, when we are talking about low ductility, this is DCL, low ductility. We are talking of a structure whereby it is not able to dissipate the energy sufficiently. And so this can result to a sudden collapsing of the building because it is not able to dissipate the energy efficiently. Now, when we talk about medium ductility, we are talking about a situation whereby the structure can partially undergo elastic deformation due to the fact that it can to some extent dissipate the seismic energy. So that means you are not going to have this sudden collapsing of the structure because it is at least going to go some plastic deformation before the final collapsing. Now, again, when you talk of this one, the high structural ductility class, we are talking a situation whereby the structure is able to fully dissipate the seismic energy effectively, such that now it will be able to go through plastic deformation effectively, and this is what we call the high ductility class. And according to Eurocode, they have been given different coefficients. For low ductility class is 1.5, for medium is 3, and for high it's normally 4.5 to about 5. So that's good to understand. So we proceed to the next step, which is now the next part here, the structure regularity. And when we talk about structure regularity here, we are talking about how best the structure can dissipate the mass, the mass and the stiffness to the plan and the elevation of the structure. And in our case, we are saying that our structure is regular in elevation. So we are going to select this. About the mode of analysis, you can choose either of this and it's going to work. So we go to the next one. So here we have fundamental period. Now fundamental period, as I have mentioned, according to Eurocode 8, is a product of, it is actually the time taken by the building to make one complete oscillation when it's subjected to the lateral forces of seismic. Now in this case we are talking about Eurocode 8, and we should understand how we calculate that. So we normally take, as you can see here, fundamental period. That's a Eurocode A clause 4. We have this is normally calculated as 3/4 the height of the building multiplied by the structural system coefficient, this one, and it's normally, this structural coefficient is normally 0.075 for RC frames and 0.085 for steel frames. So it's good to understand all this. Now, so in our case, we are going to select our structure here. It is a concrete movement resisting frame, and the software is going to calculate by its own. And the same thing here. And then after that, we proceed to the next. So we have another thing here called the behavior factor, and in the Eurocode all this has been described. The behavior factors, it is always important to refer to your Eurocode. You have all this have been defined, the software has defined them. Then you go to the next, and in this case now we have the load cases to include, and it is important for you to also get to capture something here called the importance factors. We normally have these categories 1, 2, 3, and 4, and because we chose class 3, this one, that's why you are seeing our software here is selecting, if you go back, 1.2. all right, so let's proceed. So here we include all this self weight. We go to self weight of the slab, dead load, and also the imposed. Now here we should consider 30%, which is normally 0.3. So we should edit this according to the code, Eurocode 0.3. And then we go to the next part. Here we have different localization. Localization is referring to where the seismic is going in that particular structure. So in this case, we have Breton and structural elements, and these are referring to these masonry buildings that are normally made of masonry, or maybe RC structures that are not really framed structures. And again, we also have this, the next one, which is called the ductile non-structural elements, and according to the the Eurocodes and also how this software interprets this, it is important for you to get to understand that when we are talking about the ductile and structural elements, we are referring to the framed structures that have partition walls. All right. And now, when we talk about no non-structural elements or not interfering, we are talking about the framed structures that are open without partition walls. So it is important to understand all this because it makes the basis for your design. Now, so in this case, we are going to consider ductile non-structural elements. And this is good to understand because there is also the way the software gets to interpret this. Because, for example, when you talk of low ductility or like, sorry, the brittle structural element, the first one here, that is to tell you that it is a structure with a low ductility. That means it has a very low capacity to dissipate the seismic energy. And in this case, we are likely to have the structure collapsing suddenly. On the other hand, when you talk of the ductile and structural elements, we are talking of a structure like I've mentioned, a framed structure with some partition walls. So it is always very important to get to understand all this because there is the way the software gets to interpret this. So if you don't get to understand this, it is going to be very hard for you to proceed with the correct design. And that's why it is important to always get to understand even what it means to do with localization because there is the way the software interprets all this and tells you how the structure interacts with all these kind of different elements. So for example, now when you talk of brittle and structural elements, as I've mentioned, it's good to understand how does the software interpret this, because for this case, normally the software assumes that the main structure is brittle and the non-structural elements like the walls and the partition and other elements like that's like facades and all that are present and may interact, or like they may interact with the structure. So in this case, it assumes that these elements do not add any lateral strength but can change stiffness slightly. So the best time to use this kind of option is now when we have, like I've mentioned, the masonry frames or old RC structures or any structure with brittle behavior and that has walls that might attract some seismic forces. So now when you talk of the other one, the ductile and structural elements, what you need to understand is that the main structure is normally ductile and can dissipate energy effectively. And the software in this case considers that the non-structural elements may participate lightly in stiffness, but the structure ductility dominates. So that is to tell you that in this case, you are supposed to consider these modern framed structures that are ductile and have this kind of internal partitions or lightweight masonry walls. And again, it's also good to understand how does the software interpret when it comes to the third option, no non-structural or not interfering. So that is to tell you here that the structure is designed without any significant non-structural elements, or they do not affect seismic behavior at all in any way. So in this case, TSD will always ignore walls and partitions. So for this kind of a scenario, if you can consider like a clean RC frame without any infill walls or steel frame or any fully open plan buildings. So it's important to understand all this. So in this case, we are going to take the ductile and structural element, and after that we go to finish. Now after we click the finish button, we go to the next one. Here we are supposed to define the combinations. We have three options: operating, final, and election. So erection is referring to the construction stage of the structure. Now the operation is referring to when the building is in use. That's like what we call the serviceability limit state. And on the other hand, we have the final. The final is when the building is now subjected to extreme loads. So, and in this case, because we are designing the building against collapsing, we should always select final. All right. So then we go to the next. And after this, we can select here, go to the next, then you finish. And once you do this, you are going to come here to the load cases, and you go to combinations, load cases, and you can see you have defined the seismic in direction 1 and direction 2, and seismic accidental torsion. So now after this, you go to the combinations. You can see you have all your combinations final for the seismic. All right, and then you have the envelope here. That one you can define later. So what you're supposed to do now, before you generate your complete load combination, you should always first of all define your weight loads. And to do that, you should make sure that you have your what we call the wall, or the wall panels where the weight is acting on the building. So we should activate them here, because I had already defined them. To draw them, it's very easy. If you delete this one and we redraw it, you could get to understand how you go about this. Just click here, then you can click here, then you have it. So that's how you do it. I have defined them in all directions. You can see I've defined all this, the wall panels where the weight action is going to be executed on the building. So after this, what you do is go to load, then you go to weight load, then you have the weight wizard, and we are going to select, you can see we have different directions. We have 180, we have 90 degrees, and we have this 270 degrees. So in our case, what we are going to do, we are going to define them in all these directions. And in this case, what you're going to do is that we are going to take data for each direction, because we have all these other options here, and it's important for you to consider the meteorological data that you have in your country, so that you can use that with velocities that are provided there. So in this case, we are going to use this, and now you proceed with the next step. This is where you can define your weight velocities and all this. For this, I'm going to use this depending on the place where I am. So go to the next, and here we have all this. We have these terrain categories. In our case, we have the building is in the up country, so we are going to leave it like this. You can always select the option. We have the sea, the town, and all that. Then you go to the next, and then you have holographic features. So in our case, we don't have any, and so we are going to the next part. And then we have this calculations, then we finish. Then after this, what we are supposed to do, we're supposed to go to the same place again,
And here we have this wizard here telling you update the width load zones. If it is necessary, you can change all this. Now let's go to the next part here, width load cases. So now here you go by automatic generation. So you click here and you have all this here. These are the load cases that are defined. We have just defined, and so we click OK, and they have been generated. So if we go now to load cases, we can see our width loads here, all of them. All right, and now we have our seismic loads and our normal loads here. So once you have all this, now you can proceed with combinations, and you can now come and generate the combinations, or what we have currently is the seismic combinations. Now we want to generate the full load combination. So you click here, you go to generate. Here you can always go by final. Here we select this, the first one and this one, and we have these seismic combinations, and you can see how it has been defined here. And normally you know that Eurocode normally considers seismic as accidental combination actions. So you can also tick this here and you have this. So in this case you can tick all of them and you go to final, the next, then you go to the next, and these are the combinations. Then you go to the next is service combinations. Then you go to the next part. Width directions have been defined here, so you can always choose the ones that you want, in which direction you want. For example, here we have the positive direction, and these ones are for the direction 0. So you can choose several of them that the software is going to use. So in this case, I'm going to use this one, 0 direction. Also select for the 90 direction, and also here maybe for the 180 direction you can also select. You go to the width direction, you can select again, and the same here in the other direction. You can quickly select all this, then you go to the next. You can select here direction 1, direction 2, and you go now to the next, you finish, and the software has generated all your load cases here. There are quite a number. After this, what you can do now is, now you can go to the envelope and define your load envelope. So here you can go to add, select this, and you select the ones that you want to add. You can select now this. You don't have to include everything. So after this, you can go click OK, and now when you come here to combinations, you can see your combinations here. And now when you come to the envelope, you can see your envelope here. So after this, what you're supposed to do is to run your analysis, and you go proceed with checking all that, and we are going to do that in our next video. Thank you for watching, and subscribe for more videos. Thank you for your time.